Right now, trillions of invisible particles are passing through your body without you ever noticing. These ghostly travelers, called neutrinos, are some of the most mysterious inhabitants of our universe. Born just seconds after the Big Bang, they've been silently streaming through space for over 13 billion years, carrying secrets from the dawn of time itself. Today, we're diving into the Cosmic Neutrino Background, an ancient sea of these elusive particles that fills every corner of the cosmos. What makes them so hard to detect? Why do they defy the laws of physics as we know them? And could they hold the key to understanding dark matter, the fate of the universe, or even the existence of other dimensions? Over the next 25 mysteries, we'll uncover the mind-bending puzzles hidden within this invisible neutrino ocean, from their role in shaping galaxies to their potential connection with quantum gravity. Strap in, because the answers might just rewrite everything we thought we knew about reality. Now, let's peel back the layers of time to uncover the very first mystery, the origin of the Cosmic Neutrino Background. Picture the universe in its infancy, just 1 second old. The cosmos was a seething, dense soup of particles, hotter than the core of a star. In this chaos, neutrinos were born, flooding space in unimaginable numbers. But as the universe expanded and cooled, something extraordinary happened. These neutrinos suddenly broke free, decoupling from matter like ghosts slipping through a closing door. This moment, known as neutrino decoupling, left behind a faint echo, the Cosmic Neutrino Background, a relic so ancient it predates even the cosmic microwave background by hundreds of thousands of years. Yet, this neutrino sea isn't just an older sibling to the microwave afterglow we know so well. It's colder, far more elusive, and packed with unanswered questions. Why does its temperature sit at just under 2 degrees above absolute zero? And why do its density and distribution still baffle scientists? Some theories suggest hidden interactions with dark matter or unknown particles could be at play. Others propose that the very fabric of space-time might have imprinted subtle distortions on these primordial neutrinos. What's clear is that the Cosmic Neutrino Background isn't just a fossil, it's a living puzzle. Unlike the cosmic microwave background, which paints a detailed picture of the universe's toddler years, the neutrino background whispers secrets from its first breath. Decoding those whispers could rewrite our understanding of everything from particle physics to the birth of the cosmos itself, and that's just the beginning. Now, let's tackle the next head-scratcher: why are neutrinos so incredibly hard to catch? Imagine trying to grab smoke with your bare hands. That's what detecting neutrinos feels like for scientists. These particles barely interact with anything at all. They zip through planets, stars, even you, without leaving a trace. A single neutrino could pass through a light year of solid lead without bumping into a single atom. That's how ghostly they are. This makes studying the Cosmic Neutrino Background a monumental challenge. While the cosmic microwave background gives us crisp snapshots of the early universe, the neutrino version is like trying to hear a whisper in a hurricane. To even attempt it, researchers rely on massive detectors buried deep underground or encased in ice, like the Ice Cube Observatory in Antarctica. Ice Cube uses thousands of sensors to catch the rare moment a neutrino crashes into an atom, creating a faint flash of light. But here's the catch: it only works for high-energy neutrinos, not the ultra-low-energy ones from the Cosmic Neutrino Background. Even our most advanced tools are like using a net with holes too big to catch the smallest fish. Some proposed experiments aim to change that, like hunting for subtle distortions neutrinos leave in other cosmic signals. But for now, the Cosmic Neutrino Background remains just out of reach, teasing us with secrets we can't quite grasp. And that's what makes it one of the most tantalizing puzzles in physics. Now, here's something that doesn't add up: the missing energy of neutrinos in the Cosmic Neutrino Background. Scientists have calculated how much energy these particles should have based on what we know about the early universe. But when they compare those predictions to actual observations, the numbers don't match. It's like expecting a certain amount of water to flow from a tap, only to find a trickle instead. This discrepancy isn't just a small hiccup, it could be a sign of physics beyond our current understanding. One possibility is the existence of sterile neutrinos, a hypothetical type of neutrino that doesn't interact with matter at all, not even through the weak force. If they're real, they could be soaking up some of that missing energy, hiding it from our detectors. Another wild idea, extra dimensions. Some theories suggest that neutrinos might occasionally slip into higher dimensions we can't perceive, taking a portion of their energy with them. Either way, this energy gap is more than just a puzzle, it's a potential window into new physics. Solving it could rewrite parts of the standard model or even reveal hidden layers of the universe. For now, though, the missing neutrino energy remains one of the Cosmic Neutrino Background's most intriguing mysteries, teasing us with clues we're still learning how to read. Now let's turn our attention to another cosmic puzzle, the mysterious connection between neutrinos and dark matter. Dark matter makes up about 27% of the universe, yet we've never directly detected it. We only know it's there because of its gravitational effects on galaxies and galaxy clusters. So where do neutrinos fit into this? Neutrinos are ghostly particles that barely interact with matter, and dark matter is, well, even more elusive. Some scientists wonder if neutrinos could actually be a piece of the dark matter puzzle. The problem: neutrinos move too fast to explain all of dark matter's behavior. They're what we call hot dark matter, while most of the missing mass in the universe seems to be cold, slower, and heavier. But here's where it gets interesting. What if neutrinos interact with dark matter in ways we haven't discovered yet? Maybe they exchange some hidden force, or perhaps there's a heavier, slower cousin of the neutrino we haven't found, one that could account for more of dark matter's effects. Experiments like the upcoming Deep Underground Neutrino Experiment, or DUNE, might help us find answers by studying neutrino behavior with unprecedented precision. This mystery isn't just about filling in gaps, it's about uncovering whether two of the universe's biggest unknowns are secretly linked. If they are, it could reshape our understanding of everything from galaxy formation to the fundamental laws of physics. For now, the relationship between neutrinos and dark matter remains one of the Cosmic Neutrino Background's most tantalizing enigmas. Now let's dive into another head-scratcher: the neutrino mass hierarchy problem. You'd think figuring out how much neutrinos weigh would be straightforward, but nature loves to keep us guessing. The trouble is, we know neutrinos have mass, but we don't know exactly how that mass is arranged. Are they stacked like a normal ladder, with the lightest at the bottom and heaviest at the top? Or is the order flipped, with the lightest neutrino actually sitting in the middle? This isn't just some tiny detail, it's a huge deal for physics. The way these masses are ordered could tell us whether neutrinos behave like other particles, or if they're playing by entirely different rules. And here's where the Cosmic Neutrino Background comes in. This ancient sea of neutrinos left over from the Big Bang might hold the key. If we could measure how these primordial neutrinos interact with matter, or how they've influenced the universe's expansion, we might finally crack the code. Experiments like the upcoming Jiangmen Underground Neutrino Observatory, or JUNO, are designed to tackle this very question. By studying how neutrinos change flavors as they travel, scientists hope to pin down their mass hierarchy once and for all. Solving this puzzle wouldn't just tidy up our particle physics models, it could reveal deeper truths about how the universe structures itself at the most fundamental level. For now, the neutrino mass hierarchy remains one of the Cosmic Neutrino Background's most stubborn mysteries, but every new discovery brings us closer to an answer. Now, let's turn our attention to an even bigger cosmic puzzle: how the Cosmic Neutrino Background might hold secrets about the universe's explosive infancy. Picture this, in the first fraction of a second after the Big Bang, the universe didn't just expand, it ballooned at an unimaginable rate, a process called cosmic inflation. This rapid stretching smoothed out the cosmos and planted the seeds for everything we see today. But here's the twist, inflation happened so early that its direct fingerprints are incredibly faint. That's where neutrinos come in. These ghostly particles, born just seconds after inflation ended, could carry subtle echoes of that primordial expansion. Think of them as cosmic tape recorders, preserving whispers from a time when the universe was smaller than a grain of sand. The problem, those whispers are drowned out by billions of years of cosmic noise. The cosmic neutrino background is like a faded photograph from the dawn of time. Its details blurred but not entirely lost. Scientists suspect that if we could decode the patterns in this neutrino sea, we might spot tiny ripples, anisotropies left behind by inflation. These ripples could reveal whether inflation was driven by a single force or a chaotic interplay of energies, but detecting them is like trying to hear a pin drop in a hurricane. Current telescopes can't see the CNB directly, and even future observatories will need to filter out interference from other cosmic signals, yet the stakes couldn't be higher. If the cosmic neutrino background does bear inflation's mark, it could answer one of cosmology's biggest questions: what launched the universe into hyperdrive? For now, this mystery remains locked in those faint, ancient neutrinos, waiting for the right tools and the right minds to set it free. Now, let's dive into one of the most fascinating quirks of neutrinos, their ability to shapeshift. Imagine ordering vanilla ice cream, only to watch it morph into chocolate and then strawberry as you take each bite. That's essentially what neutrinos do as they travel through space, switching between three flavors: electron, muon, and tau, in a phenomenon called neutrino oscillations. This cosmic sleight of hand happens because neutrinos have mass, albeit tiny, and their quantum states mix as they zip across the universe. But here's where it gets tricky for the cosmic neutrino background. These particles have been journeying for over 13 billion years, meaning they've had plenty of time to oscillate. The big question is, has all that flavor swapping scrambled the original composition of the CNB? Primordial neutrinos, fresh from the Big Bang, should have started in a specific ratio of flavors. But if oscillations altered that mix, it could blur the snapshot we're trying to study. Some theories suggest these changes might even erase critical clues about the early universe, like temperature variations or hints of exotic physics. On the flip side, oscillations could also imprint new patterns, subtle wrinkles that reveal hidden properties of neutrinos, like their exact masses or how they interact with gravity. Detecting these shifts in the CNB is like trying to reconstruct a faded recipe where the ingredients keep changing. Current experiments like Super Kamiokande observe oscillations in lab-produced neutrinos, but the ancient ones in the CNB are far more elusive. If we could compare their flavors today to predictions from the early universe, we might solve two puzzles at once: how neutrinos behave over cosmic timescales and whether they've rewritten their own history. For now, the cosmic neutrino background's oscillations remain a tantalizing enigma, one that could either obscure the universe's secrets or hand us a whole new set of clues. Either way, it's a reminder that even the ghostliest particles love to keep us guessing. Now, let's turn our attention to one of the biggest head-scratchers in cosmology: why our universe is made mostly of matter with almost no antimatter left. If the Big Bang created equal amounts of both, where did all the antimatter go? This is where the cosmic neutrino background might hold a crucial piece of the puzzle. Neutrinos could be key players in this cosmic imbalance thanks to something called CP violation. In simple terms, CP violation means that particles and their antimatter counterparts don't always behave symmetrically. For neutrinos, this could mean they interact slightly differently with matter versus antimatter, tipping the scales in favor of the matter we see today. The CNB, as a fossil from the universe's earliest moments, might still carry traces of this asymmetry. If neutrinos participated in processes that favored matter over antimatter, their leftover background could encode subtle hints about how the imbalance happened. Some theories even suggest that heavy, right-handed neutrinos, ones we haven't detected yet, could have decayed unevenly, producing more matter than antimatter in the process. The challenge is untangling these clues from the CNB's faint signals. Experiments like T2K in Japan are already hunting for signs of CP violation in modern neutrinos. If they find it, it could mean the CNB played a role in shaping the matter-dominated universe we live in. So, while we're still piecing together the full story, the cosmic neutrino background offers a tantalizing possibility that the ghostliest particles in existence might hold the answer to one of cosmology's most profound mysteries. And if they do, it could rewrite our understanding of how everything came to be. Now, here's something that might surprise you: the cosmic neutrino background isn't perfectly uniform. Some patches of this ghostly sea are slightly warmer or cooler than others, and these temperature anomalies could be hiding secrets about the universe's turbulent infancy. Think of it like finding unexpected hot and cold spots in a cup of coffee long after it's been stirred. These irregularities shouldn't exist if the early universe was perfectly smooth, so what caused them? One possibility is that hidden forces, maybe even unknown particles, interacted with neutrinos in ways that left uneven imprints. Another idea is that violent events in the first seconds after the Big Bang, like quantum fluctuations or cosmic strings, created ripples in the neutrino sea, freezing into place as the universe expanded. These anomalies aren't just random noise. If we can map them precisely, they might reveal clues about how matter clumped together to form the first galaxies, or whether dark energy was already shaping the cosmos in its earliest moments. The challenge, detecting these subtle variations, requires instruments far more sensitive than anything we have today. But future observatories like next-generation neutrino telescopes or space-based detectors could finally give us a clear picture of these cosmic fingerprints. So while the CNB's temperature quirks might seem like small details, they could be the key to unlocking massive questions about the universe's birth and evolution. And that's what makes this mystery so thrilling. Even the faintest whispers from the neutrino background might carry echoes of the cosmos's most dramatic moments. Now, let's turn our attention to another cosmic puzzle: how neutrinos might have shaped the birth of black holes in the early universe. Picture this: the cosmos was a chaotic, dense soup of particles just moments after the Big Bang, and neutrinos were everywhere, zipping through space almost undisturbed. But could these ghostly particles have played a hidden role in pulling together the first black holes? Here's the idea. In the early universe, vast clouds of primordial gas were collapsing under their own gravity, eventually forming the seeds of black holes. But gravity alone might not have been enough to trigger this collapse quickly. Enter neutrinos. If these particles had even a tiny bit more mass or interacted slightly more with matter than we think, they could have nudged those gas clouds, adding just enough gravitational pull to kickstart the process. Think of it like a gentle push on a wobbly stack of blocks. Neutrinos might have been the unseen hand that tipped the scales. There's another twist. Some theories suggest that the cosmic neutrino background could have created subtle density variations in the early universe, like ripples in a pond. These ripples might have acted as blueprints, guiding where matter clumped together and where black holes eventually formed. If true, neutrinos wouldn't just be bystanders, they'd be architects, shaping the universe's most mysterious objects from the shadows. Of course, proving this is a monumental challenge. Black holes from this era are long gone or hidden, and neutrinos leave almost no trace. But astronomers are hunting for clues in the echoes of ancient gravitational waves or the faint glow of the first stars. If we can piece together how these early black holes formed, we might finally uncover whether neutrinos were silent partners in their creation. So while they're famously elusive, neutrinos could hold the answer to one of cosmology's biggest questions: how the universe's darkest monsters came to be. And that's a mystery worth chasing. Now, shifting our gaze to an even deeper layer of the cosmos, let's explore how the cosmic neutrino background might hold clues to one of physics' greatest quests, unifying gravity with quantum mechanics. Quantum gravity has long eluded scientists, but neutrinos, with their ghostly nature, could be the key to cracking this puzzle. Here's why. At the tiniest scales, spacetime might not be smooth as Einstein imagined, but instead grainy like sand on a beach. If that's true, neutrinos traveling billions of light years almost untouched could pick up subtle bumps or twists from this granular structure. Think of it like rolling a marble over a bumpy surface. Even if the bumps are microscopic, the marble's path might reveal their presence. Neutrinos, in this case, could be our cosmic marbles, carrying hints of spacetime's hidden texture. Some theories suggest that the way neutrinos oscillate, changing flavors as they travel, could be influenced by quantum gravity effects. If we detect unexpected patterns in the cosmic neutrino background, it might mean neutrinos are interacting with spacetime's tiny grains. That would be groundbreaking, offering the first experimental glimpse into how gravity works at the quantum level. Of course, the challenge is immense. Quantum gravity's effects are vanishingly small, and neutrinos are notoriously hard to pin down. But next-generation detectors, like ultra-sensitive neutrino telescopes or space-based observatories, might finally catch these whispers of quantum spacetime. If they do, the cosmic neutrino background could go from a relic of the past to a roadmap for the future, guiding us toward a theory of everything. So while neutrinos might seem like faint cosmic whispers, they could be shouting the secrets of quantum gravity. And that's a conversation worth tuning into. Now, let's dive into another fascinating layer of the cosmic neutrino background, its potential role in shaping the universe's magnetic fields. Picture the cosmos as a vast ocean with neutrinos flowing like an invisible sea. These particles, though nearly massless, carry a tiny electric charge known as their weak charge. It's so faint that for decades, scientists assumed it couldn't possibly leave a mark on the universe. But what if, collectively, this sea of neutrinos generates forces we've overlooked? Here's the intriguing possibility. As neutrinos stream through space, their weak charges might interact ever so slightly with charged particles like electrons or protons. Over billions of years, these minuscule interactions could add up, creating ripples of magnetic fields on cosmic scales. Imagine dropping a single grain of sand into a still pond. It barely makes a splash. But trillions of grains over eons could stir the water into motion. Similarly, neutrinos might be the hidden architects of magnetic fields that stretch across galaxies. Some theories suggest these neutrino-generated fields could explain mysteries in our universe, like why certain galaxy clusters have unexpected magnetic signatures. Others propose that the cosmic neutrino background's influence might even seed the magnetic fields we see today, acting as a cosmic blueprint, but proving this is another challenge. Detecting such subtle forces requires instruments sensitive enough to distinguish neutrino-driven effects from other cosmic noise, yet the implications are staggering. If neutrinos do shape magnetic fields, it would mean these ghostly particles don't just passively fill space, they actively sculpt it. Future experiments, like advanced radio telescopes mapping the universe's magnetic web, might finally uncover this hidden connection. Until then, the neutrino sea remains a tantalizing frontier, whispering hints of forces we're only beginning to imagine. And with that, we're ready to explore how these elusive particles might shape the very fabric of galaxy clusters, a mystery that takes us even deeper into the cosmic unknown. Now, let's turn our attention to the vast gatherings of galaxies and how the cosmic neutrino background might be quietly shaping their destiny. Galaxy clusters, the universe's largest structures, are held together by gravity, but there's more to the story. Neutrinos streaming through space in unimaginable numbers could be exerting a subtle yet powerful influence on how these colossal assemblies form and evolve. Think of galaxy clusters as cities in the cosmos, with galaxies as buildings and dark matter as the unseen framework. But what if neutrinos are the invisible architects subtly guiding the construction? Their sheer abundance means that even their tiny masses add up. As they move through these clusters, they could create a kind of pressure that affects how galaxies settle into place. Some scientists suggest this neutrino pressure might explain why certain clusters have unexpected shapes or distributions of galaxies, like a gentle cosmic hand nudging things into position. Then there's the idea of dark scaffolding. Just as steel beams support a skyscraper, neutrinos might provide an unseen structure that helps galaxy clusters maintain their form. Their constant motion could weave a delicate web of influence, shaping the paths of galaxies over billions of years. This wouldn't be obvious to telescopes, but subtle patterns in how clusters evolve might hold clues. The challenge, of course, is proving it. Neutrinos interact so weakly that their effects are drowned out by gravity and dark matter. Yet advanced simulations are starting to reveal how neutrino flows might leave faint fingerprints in the way clusters grow. Future telescopes like the Vera Rubin Observatory could spot these subtle signatures by mapping the universe's large-scale structure in unprecedented detail. If neutrinos do play this hidden role, it would mean they're not just passive bystanders in the cosmos, they're active participants in building its grandest structures. And with that, we're ready to ponder an even deeper question. Could the cosmic neutrino background hold secrets about time itself? But here's something even more mind-bending. What if the cosmic neutrino background holds clues about time itself? We all experience time moving forward from past to future, but physics doesn't actually explain why. The universe's arrow of time is tied to something called entropy, a measure of disorder that always increases. And the CNB, with its incredibly low entropy state frozen in from the Big Bang, might be hiding secrets about why time flows the way it does. Picture the early universe as a tightly wound spring full of order and energy. As it expanded, that spring unwound, creating the disorder we see today. Neutrinos, born in that ultra-ordered environment, carry a snapshot of that moment. Their distribution, cool, smooth, and uniform, is like a fossil of the universe's lowest entropy state. Some physicists think this neutrino fossil could be the reason time has a direction at all. Without that initial order, there'd be no arrow pointing forward. Now, here's where it gets wild. If neutrinos encode this thermodynamic history, they might also hold answers to one of cosmology's biggest puzzles: why the early universe was so organized in the first place. Was it pure chance, or does the CNB hint at deeper laws we haven't discovered yet? Even stranger, if we could somehow rewind the neutrino background, would time reverse too? Of course, untangling this isn't easy. Neutrinos are notoriously hard to study, and their connection to entropy is still theoretical. But future experiments might look for tiny irregularities in the CNB that reflect how disorder spread in the early cosmos. If found, these patterns could rewrite our understanding of time's origins, and maybe even reveal whether time's arrow is a universal rule or just a quirky feature of our corner of reality. With that, we're left staring at another cosmic riddle. If neutrinos really do shape time's flow, what other invisible threads are they weaving through the fabric of existence? Now, let's venture to the very edges of the cosmos, where things get even stranger. Imagine the universe having a boundary, not like a wall you could touch, but a frontier where the rules might bend. And here's the twist. What if the cosmic neutrino background forms a kind of neutrino wall at this edge? Think of it like a cosmic shoreline where the ocean of neutrinos meets, well, whatever lies beyond. Some theories suggest the CNB could pile up there, becoming denser as neutrinos accumulate over billions of years. If that's true, this neutrino barrier might act like a filter, trapping particles or even bending spacetime in ways we can't yet detect. But why would neutrinos cluster at the edge? One idea ties back to the Big Bang. As the universe expanded, neutrinos raced outward at nearly the speed of light. Over time, those at the very edge could have slowed or stacked up against whatever lies outside our observable universe. If they did, this wall might hold clues about the universe's shape. Is it infinite, or does it have a hidden structure we've never seen? Even wilder, if the CNB is denser at the edge, it could warp the path of other particles or light passing through it. Astronomers might one day spot distortions in distant galaxies or cosmic rays that hint at this invisible barrier. And if it exists, it could redefine our understanding of cosmic boundaries, not as empty voids, but as dynamic neutrino frontiers. Of course, this is all speculation for now. The universe's edge is beyond our observational reach, and neutrinos are already ghosts to detect, but the possibility alone stretches our imagination. Could the CNB be the universe's way of marking its territory? And if so, what or who might lie on the other side? This mystery pulls us deeper into the unknown, where every answer only reveals more questions. And as we'll see next, the cosmic neutrino background might not just shape the universe's edges, it could also whisper secrets about dimensions beyond our own. Now, let's stretch our minds even further into the realm of extra dimensions. String theory, one of the most ambitious frameworks in physics, suggests our universe might have more than the 3 dimensions of space and 1 of time we experience. And here's where the cosmic neutrino background comes in. Could its subtle anomalies be whispers from these hidden dimensions? Picture neutrinos as cosmic detectives. Their ghostly nature means they barely interact with ordinary matter. But what if they occasionally slip into higher dimensions? If compactified dimensions, those curled up too small for us to see, exist, neutrinos might be the only particles nimble enough to traverse them. This could explain why some neutrinos seem to vanish or behave unpredictably in detectors. They're not disappearing, they might be taking detours through dimensions we can't perceive. The math behind this is mind-bending. In string theory, vibrations in these extra dimensions could alter how neutrinos move or oscillate between flavors. If the CNB carries imprints of these vibrations, it might reveal patterns that don't fit our standard models. Imagine finding a fingerprint in the neutrino sea that points to a 5th or 6th dimension. It would rewrite physics as we know it. But how could we spot these echoes? One clue lies in energy discrepancies. If neutrinos leak into higher dimensions, they might return with slightly less energy, leaving gaps in our observations. Experiments like IceCube or future quantum sensors could hunt for these tiny deficits, like listening for faint echoes in a vast canyon. Of course, this idea dances on the edge of science and speculation. Extra dimensions remain theoretical, and proving their existence through neutrinos would require breakthroughs in both theory and technology. Yet the possibility is electrifying. The CNB might not just be a relic of the past, it could be a bridge to dimensions beyond our grasp, waiting to be decoded. And as we peel back these layers, another question arises. If neutrinos can traverse hidden dimensions, what else might be lurking there? The answers could redefine reality itself. Now, let's turn our attention to one of the biggest puzzles in modern cosmology, the Hubble tension. This isn't about a telescope feeling stressed. It's a glaring mismatch in how fast our universe is expanding. On one hand, we have measurements from the cosmic microwave background, suggesting a certain expansion rate. On the other, observations of nearby galaxies and supernova point to a noticeably faster pace. Scientists have scratched their heads over this for years, and here's where neutrinos might step in as unexpected peacemakers. Think of the cosmic neutrino background as a silent witness to the universe's expansion. These particles have been around since the beginning, barely interacting with anything, yet subtly influenced by the fabric of spacetime itself. If neutrinos have properties we haven't fully accounted for, like slight variations in mass or interactions with dark energy, they could be tweaking the expansion rate in ways that explain the discrepancy. One intriguing possibility involves neutrino energy. If these particles lose or gain even a tiny amount of energy over billions of years, it could affect how they contribute to the universe's overall density. And since density directly influences expansion, this might reconcile the conflicting measurements. Imagine neutrinos as invisible dials, fine-tuning the cosmos in ways we're only beginning to measure. Then there's the role of sterile neutrinos, hypothetical particles that don't interact via any known force except gravity. If they exist, they could be diluting the universe's energy density early on, altering the expansion rate we infer from the cosmic microwave background. It's like discovering a hidden ingredient in a recipe that changes how the entire dish turns out. Of course, this isn't a done deal. Proving that neutrinos hold the key to the Hubble tension would require sharper observations and tighter theoretical models. Upcoming projects like the Vera Rubin Observatory or next-generation neutrino detectors could provide the data we need. But the idea is thrilling. The same ghostly particles that baffle us in labs might also be the missing link in understanding the universe's expansion. And as we piece together this cosmic puzzle, another layer emerges. If neutrinos can help resolve the Hubble tension, what other secrets might they reveal about the forces shaping our universe? The answers could be hiding in plain sight, woven into the faint whispers of the cosmic neutrino background. Now, let's tackle another head-scratcher, the case of the missing neutrinos in the cosmic neutrino background. You'd think after traveling billions of years undisturbed, all three known neutrino flavors, electron, muon, and tau, would be equally represented, but something's off. Measurements suggest some flavors are mysteriously scarce, as if part of the neutrino population has gone into hiding. So where did they go? One possibility is flavor transformation. Neutrinos are shape-shifters, oscillating between types as they travel. Over cosmic distances, this could mean some flavors effectively vanish from our detectors, blending into others like chameleons in a forest. But here's the twist: the math doesn't fully add up. Even accounting for oscillations, there's still a gap, hinting at something more exotic at play. Enter sterile neutrinos, the hypothetical fourth flavor that refuses to interact with anything except gravity. If these exist, they could be siphoning off some of the missing neutrinos, pulling them into a shadow realm of physics we can't yet observe. Picture a cosmic game of hide and seek where the seekers, our detectors, are blind to an entire team. Then there's the wild card, quantum decoherence. In the chaos of the early universe, neutrinos might have lost their quantum coherence, scrambling their flavors beyond recognition. It's like trying to read a book after someone shuffled all the pages. The story's still there, but the pieces don't line up the way we expect, of course. Proving any of this is a monumental challenge. Current detectors are tuned to catch the neutrinos we know, not the ones we don't. Future experiments, like those hunting for sterile neutrinos or probing quantum gravity effects, might finally crack the case. Until then, the missing neutrinos remain one of the CNB's most tantalizing loose ends, a clue that could rewrite the rules of particle physics or reveal an entirely new layer of reality. And if that's not enough to ponder, consider this. What if the missing neutrinos aren't missing at all? What if they've morphed into something else entirely, a form of matter or energy we haven't even imagined yet? The cosmic neutrino background, it seems, still has a few tricks up its sleeve. Now, let's shift gears to one of the most puzzling questions in modern cosmology. Could the cosmic neutrino background actually help us crack the mystery of dark energy? We know dark energy is pushing the universe to expand faster, but what it actually is remains a total enigma. Here's where neutrinos might step in as unexpected detectives. Think of the CNB as a vast, ancient net stretching across the cosmos. If dark energy interacts with neutrinos even faintly, it could leave subtle fingerprints in how these particles move or cluster over time. Imagine tossing a pebble into a still pond. The ripples would tell you something about the pebble's size and weight. Similarly, distortions in the neutrino background could hint at dark energy's hidden properties. Some theories suggest neutrinos might act as a bridge between dark energy and ordinary matter. If dark energy exerts a tiny force on neutrinos, it could slightly alter their speeds or trajectories across billions of years. Detecting these minute changes would be like spotting a single shifted grain of sand on a beach. But next-generation observatories like ultra-sensitive neutrino telescopes or space-based gravitational wave detectors might just have the precision needed. Then there's the wild idea that neutrinos themselves could influence dark energy. If certain neutrino flavors decay into exotic particles, they might release energy that fuels dark energy's expansion. It's a long shot, but if true, it would mean the CNB isn't just a relic. It's an active player in shaping the universe's fate. Of course, the big hurdle is proving any of this. Dark energy's effects are incredibly weak, and neutrinos are notoriously hard to pin down. But if we can tease out even a faint signal linking the two, it would revolutionize physics. The Cosmic Neutrino Background might be our oldest cosmic artifact and, ironically, our best shot at understanding the force that's driving the universe's future. And that brings us to another eerie possibility. What if dark energy isn't a force at all, but a side effect of neutrinos behaving in ways we haven't yet imagined? The deeper we dig into the CNB, the more it feels like a cosmic hall of mirrors full of reflections that might just lead us to the truth. But here's something even more mind-bending. What if the Cosmic Neutrino Background isn't just a silent relic, but a cosmic symphony waiting to be heard? Picture the early universe as a seething, hot soup of particles, where neutrinos weren't just drifting, they were caught in massive sound waves rippling through space. These weren't ordinary sound waves, though. They were pressure oscillations like the deep hum of a bass note vibrating through the cosmos, compressing and stretching matter in their wake. As the universe expanded and cooled, those waves froze in place, leaving faint imprints in the distribution of neutrinos. Today, the CNB could still carry those echoes, like fossilized vibrations from the universe's first seconds. The catch: we can't exactly plug in headphones to listen. Instead, scientists look for subtle patterns in how neutrinos are scattered across the sky. If those patterns match the predicted sound of the early universe, it would be like uncovering a recording of the Big Bang's aftermath, the wild part. These neutrino sound waves might hold clues about forces we've never detected. Just as a guitar string's vibrations reveal its tension, the CNB's oscillations could hint at unknown particles or interactions that shape the cosmos. Some theories even suggest these waves might have nudged dark matter into clumping, seeding the galaxies we see today. Of course, detecting this neutrino music is a colossal challenge. It's like trying to hear a whisper in a hurricane, but upcoming experiments like ultra-precise cosmic surveys or next-gen neutrino detectors could finally tune in. If they do, we might not just solve a mystery, we'd have a front-row seat to the universe's oldest concert. And that raises a haunting question. If we could truly listen to the CNB, what other secrets would its echoes reveal? The answer might rewrite our understanding of everything from the birth of atoms to the fate of the cosmos itself. Now, let's take a leap into one of the most tantalizing possibilities. Could the Cosmic Neutrino Background be a window into other universes? Imagine the CNB not just as a relic of our own universe's birth, but as a cosmic message board where multiple realities leave their fingerprints. The idea of a multiverse, countless universes bubbling alongside ours, has long been a staple of theoretical physics. But what if neutrinos, those ghostly particles, carry traces of these unseen realms? Think of it like this: if other universes exist beyond our own, they might occasionally brush against ours, leaving subtle imprints in the neutrino sea. These collisions or overlaps could create tiny irregularities in the CNB anomalies that don't quite fit our universe's expected patterns. Some theories suggest that these marks might appear as unexpected fluctuations in neutrino density or energy, like faint scars from a cosmic close encounter. The challenge, of course, is separating these potential multiverse signals from the noise of our own universe's history. It's like trying to spot a single unique grain of sand on a vast beach. But if scientists could identify these anomalies, it would be revolutionary. Suddenly, the CNB wouldn't just tell us about our past, it could hint at realities beyond our own, where the laws of physics might be entirely different. And here's where it gets even wilder. If other universes have their own neutrino backgrounds, could they be subtly influencing ours? Some models propose that gravitational waves or quantum entanglement might bridge the gap between universes, leaving echoes in the CNB. While this remains speculative, the mere possibility opens up a dizzying array of questions. Could neutrinos be the universe's way of whispering secrets about its siblings? For now, this idea sits at the edge of science, a thrilling hypothesis waiting for evidence. But as detectors grow more sensitive and our understanding of neutrinos deepens, we might one day find clues hidden in the CNB's faint glow. And if we do, it wouldn't just solve a mystery, it would redefine our place in the cosmos. Now, shifting our focus to another puzzling feature of the Cosmic Neutrino Background, let's explore those mysterious cold spots scattered across its faint glow. These regions where the neutrino sea appears unexpectedly cooler than its surroundings have scientists scratching their heads. Are these cold patches cosmic scars left behind by ancient defects in spacetime, or could they be the echoes of quantum fluctuations from the universe's earliest moments? Picture the CNB as a vast, uneven tapestry. Most of it follows a predictable pattern, but these cold spots stand out like odd stitches in the fabric. One leading theory suggests they might be relics of cosmic strings, hypothetical, thread-like defects in spacetime that formed during the universe's rapid expansion. If these strings existed, their gravitational pull could have subtly altered the distribution of neutrinos, leaving behind these chilly fingerprints. On the other hand, these cold spots might trace back to quantum fluctuations, tiny, random variations in energy that occurred during the Big Bang. Normally, these fluctuations are thought to have smoothed out as the universe expanded, but what if some left lasting imprints on the CNB? It's like finding frozen ripples in a pond long after the stone was thrown. The real challenge lies in distinguishing between these possibilities. Current detectors struggle to map the CNB with enough precision to spot these anomalies clearly. But future experiments like next-generation neutrino observatories or space-based telescopes could bring these cold spots into sharper focus. If we can decode their origins, we might unlock secrets about the universe's infancy, whether it's evidence of exotic physics or just the remnants of primordial chaos. For now, these cold spots remain one of the CNB's most intriguing riddles. They remind us that even the faintest glow from the dawn of time can hold surprises, waiting for the right tools and the right minds to uncover them. Now, let's turn our gaze toward the far future where the Cosmic Neutrino Background might hold clues about the ultimate fate of the universe itself. As the cosmos expands and galaxies drift apart, stars will burn out, black holes will evaporate, and matter itself may decay. But what about neutrinos? These ghostly particles born in the universe's first seconds could be the last witnesses to everything. Imagine a time trillions of years from now when the universe is cold, dark, and nearly empty. The cosmic microwave background, the afterglow of the Big Bang, will have faded into oblivion as space stretches its light into undetectable wavelengths. Yet the cosmic neutrino background, with its even lower energy, might persist far longer, a faint whisper from the dawn of time. Neutrinos, barely interacting with anything, could outlast protons, black holes, even the last embers of stellar remnants. They might be the final relics of a universe that has otherwise erased all traces of its fiery birth. But here's the twist: the CNB's behavior could also hint at how the cosmos will meet its end. If neutrinos have even a tiny mass, and we know they do, their gravitational influence might subtly shape the universe's expansion over eons. Some theories suggest that neutrinos could contribute to a big freeze, where the universe expands forever into icy darkness. Others speculate that their properties might tie into more exotic scenarios, like a big rip or a cyclical rebirth. The real puzzle lies in decoding what the CNB's slow fade tells us. Will its neutrinos simply drift forever in an endless void, or could they somehow seed a new cosmic cycle? Right now, we're like detectives piecing together fragments of a story written in particles nearly as old as time. Future observations of the CNB's temperature and distribution might reveal whether the universe is headed for eternal silence or something even stranger. One thing's certain, the Cosmic Neutrino Background isn't just a relic of the past. It's a time capsule carrying secrets not only about where we came from, but also where we're all ultimately headed. And that makes it one of the most profound mysteries in all of cosmology. Now, let's venture into one of the most mind-bending mysteries of the Cosmic Neutrino Background: quantum entanglement. Picture this: two neutrinos born in the same fiery instant just after the Big Bang, separated by billions of light years. Yet, if they're entangled, their fates remain mysteriously linked. A change to one could instantly influence the other, no matter how far apart they are. It's a cosmic-scale connection that defies our everyday intuition about how the universe should work. Quantum entanglement is already strange enough in labs here on Earth, where particles like electrons or photons can be linked across tiny distances. But the CNB takes this to an unimaginable extreme. If neutrinos in this ancient sea are entangled, their connections could stretch across the entire observable universe. That would mean the fabric of reality itself might be woven with invisible threads tying together particles from opposite ends of space. Why does this matter? For one, it could reshape our understanding of quantum mechanics on the grandest possible stage. Most tests of entanglement happen in controlled, small-scale experiments. The CNB, though, offers a natural laboratory where these quantum links have existed for nearly 14 billion years. Studying them might reveal whether entanglement survives over cosmic distances, or if some unknown force breaks these connections over time. Even more intriguing is what this could tell us about the early universe. If entanglement persists in the CNB, it might preserve a snapshot of how particles behaved in the first moments after the Big Bang. Were neutrinos entangled as they decoupled from the primordial soup? Could their quantum links hold clues about the universe's initial conditions? And then there's the wildest possibility of all. If entanglement spans the cosmos, could it hint at a deeper, hidden layer of reality? Some theories suggest these quantum connections might arise from extra dimensions or a fundamental network linking all things. The CNB's neutrinos, drifting silently through space, might be carrying answers we're only beginning to imagine. Of course, detecting entanglement in the CNB is a monumental challenge. These particles barely interact with anything, let alone our detectors. But future experiments like ultra-sensitive quantum sensors or space-based observatories might one day catch a glimpse of these ghostly connections. Until then, the question lingers: is the universe bound together by an invisible quantum web, written in the language of neutrinos? This mystery doesn't just stretch across space, it stretches our very understanding of reality. And that's what makes the Cosmic Neutrino Background so endlessly fascinating. Now, let's turn our gaze toward the future, where cutting-edge technology might finally crack the deepest secrets of the Cosmic Neutrino Background. Picture a new generation of detectors, so advanced they make today's instruments look like ancient telescopes. These aren't just upgrades, they're revolutionary tools designed to catch what's been nearly invisible until now. At the forefront are quantum sensors, harnessing the bizarre rules of the quantum world to spot neutrinos with unprecedented precision. Unlike traditional detectors, which rely on rare interactions, these devices could amplify the faintest signals from the CNB, almost like turning up the volume on a whisper from the dawn of time. Some prototypes even use ultra-cold atoms or superconducting materials, chilled to near absolute zero, to reduce noise and boost sensitivity. The goal: to capture the subtle fingerprints of primordial neutrinos as they pass through, untouched since the universe's first second. Then there's the dream of space-based neutrino observatories. Imagine a fleet of satellites orbiting beyond Earth's interfering atmosphere, their instruments trained on the cosmic neutrino sea. Free from terrestrial limitations, they could scan the entire sky, mapping the CNB's faint glow in ways ground-based labs never could. Projects like this are still in early planning stages, but the potential is staggering, like opening a window directly into the infant universe. But the real game-changer might lie in combining these technologies. Think of a global network of quantum sensors on Earth paired with space-based arrays, all synchronized to hunt for CNB neutrinos in unison. Together, they could triangulate signals, filter out background noise, and even test whether these ghostly particles are entangled across cosmic distances. It's the kind of collaboration that could turn the CNB from a theoretical puzzle into a detailed cosmic map. What breakthroughs could this bring? For starters, we might finally measure the exact mass of neutrinos, a tiny number with huge implications for particle physics and cosmology. Or we could spot anomalies in the CNB's temperature or distribution, hinting at unknown forces or early universe phenomena. And if entanglement is confirmed, it could rewrite textbooks on quantum mechanics and gravity. Of course, the road ahead is long. Building these detectors demands breakthroughs in engineering, computing, and funding, but the stakes, nothing less than decoding the universe's oldest hidden layer. The Cosmic Neutrino Background has kept its secrets for nearly 14 billion years. With the ultimate neutrino detector, humanity might finally start listening. Now, let's take a wild but fascinating detour. Could the Cosmic Neutrino Background be more than just a relic of the early universe? What if it's also a cosmic communication network, a hidden highway used by advanced civilizations we've yet to discover? It sounds like science fiction, but when you break it down, the idea isn't as far-fetched as it seems. Think about it. Neutrinos zip through planets, stars, and galaxies almost untouched, making them the perfect messengers. An alien civilization with technology far beyond ours might see the CNB as the ultimate communication tool, a way to send signals across unimaginable distances without interference. Unlike radio waves, which scatter and weaken, neutrino messages could travel cleanly through the universe, carrying information from one corner of the cosmos to another. But how would that even work? For starters, they'd need a way to encode information into neutrinos, perhaps by manipulating their flavors or energies in precise patterns. Imagine a neutrino-based Morse code, but infinitely more complex. Detecting such signals would require detectors sensitive enough to pick up intentional changes in the CNB's natural flow, something our current technology can't do. Yet, if another civilization has mastered this, their messages might already be washing over us, hidden in plain sight. And here's another twist: what if the CNB isn't just for communication, but also for manipulation? A sufficiently advanced species might use neutrinos to influence cosmic structures, nudging star formation or even steering the evolution of galaxies. The CNB's weak interactions could make it the ultimate stealth tool, leaving no visible trace of their engineering. It's a chilling thought that the universe's largest scale structures might bear the fingerprints of intelligence we can't yet perceive. Of course, this is all speculation. There's zero evidence that the CNB is anything but a natural phenomenon, but the possibility invites us to think bigger. If neutrinos are the universe's silent witnesses, could they also be its silent messengers? The answer, like the CNB itself, remains shrouded in mystery for now. Now, let's step back from the realm of speculation and see how the Cosmic Neutrino Background stacks up against its sci-fi counterparts. Pop culture loves to take scientific concepts and spin them into something flashy, and neutrinos are no exception. From Star Trek to The X-Files, these ghostly particles have been portrayed as everything from superweapons to alien detection tools. But how much of that is Hollywood magic and how much aligns with reality? Take Star Trek, for instance. In one episode, neutrinos are used to detect cloaked ships. A clever idea, but not exactly how they work in real life. Real neutrinos barely interact with matter, making them terrible for tracking objects. If a cloaked ship existed, neutrinos would pass right through it, leaving no trace. On the flip side, some sci-fi gets surprisingly close. Contact, the movie based on Carl Sagan's novel, imagines advanced beings using neutrino-based communication. That's not far from the theories we just explored about the CNB as a cosmic network. Then there are the outright myths. Some stories depict neutrinos as dangerous, capable of causing explosions or mutations. In reality, trillions of neutrinos pass through your body every second without a single interaction. They're harmless, so don't expect them to turn you into a superhero or blow up a planet anytime soon. But the real wonder isn't in their fictional power, it's in what they actually reveal about the universe. The CNB is a time capsule from the Big Bang, and studying it could unlock secrets about dark matter, cosmic inflation, and even the birth of galaxies. Sci-fi thrives on exaggeration, but the truth is just as thrilling. While Hollywood's neutrinos might be flashy, the real ones are quietly reshaping our understanding of the cosmos. So next time you see them on screen, you'll know where the science ends and the storytelling begins. Now, let's pull back the curtain and meet the real-life detectives behind the Cosmic Neutrino Background, the scientists who have spent decades chasing these ghostly particles. Their stories are a mix of stubborn persistence, heart-stopping breakthroughs, and the kind of frustration that only comes from hunting something nearly invisible. Take the team behind the Ice Cube Neutrino Observatory in Antarctica. Picture this, a frozen desert, temperatures plunging below -50 degrees Celsius, and a group of researchers drilling holes deep into the ice to deploy sensors. One scientist described it as trying to build a telescope blindfolded while wearing mittens. For years, they detected nothing but noise. Then, in 2013, they caught their first high-energy neutrino from beyond our galaxy, a eureka, a moment that had them dancing in the snow despite the frostbite risk. Then there's the tale of the Sudbury Neutrino Observatory in Canada, buried 2 kilometers underground in a nickel mine. The team there spent years calibrating their detector, only to discover their measurements didn't match predictions. At first, they assumed they'd made a mistake, but the anomaly held, and it led to the Nobel Prize-winning discovery that neutrinos change flavors, proving they have mass. One researcher joked, "We went looking for a typo in our math and found a new law of physics instead." But not every story has a tidy ending. Some experiments run for decades without a definitive result, like the hunt for the elusive sterile neutrino. One physicist compared it to chasing a shadow with a flashlight that keeps flickering. Yet even the failures move science forward, narrowing down possibilities and sharpening the next generation of detectors. What ties these stories together? A mix of grit and wonder. These scientists aren't just crunching numbers, they're piecing together the universe's oldest secrets, one neutrino at a time. And sometimes the biggest breakthroughs start with a simple question. Wait, that shouldn't happen, should it? Now, as we wrap up this cosmic journey, let's take a moment to reflect on the 25 mysteries of the Cosmic Neutrino Background we've explored. From its origins just seconds after the Big Bang to its potential role in dark matter, quantum gravity, and even the fate of the universe, the CNB isn't just a relic of the past, it's a key to unlocking some of cosmology's most profound questions. Each mystery we've uncovered, whether it's the missing neutrino energy or the tantalizing hints of extra dimensions, reminds us how much we still have to learn about the fabric of reality. What makes these puzzles so thrilling is that they're not just academic curiosities. They're pieces of a grander story about how the universe works, and every answer we find opens new doors to even deeper questions. The CNB is like a cosmic whisper carrying secrets from the dawn of time, and we're only just beginning to listen. So, what's next? As technology advances from quantum sensors to space-based detectors, we're inching closer to unraveling these enigmas. Maybe one day you'll wake up to headlines announcing a breakthrough that cracks one of these mysteries wide open. Until then, stay curious. The universe is full of wonders waiting to be discovered, and the next big revelation could be just around the corner. Before you go, let us know in the comments which of these 25 mysteries fascinates you the most. Is it the link between neutrinos and dark matter, or the idea of a neutrino wall at the edge of the cosmos? Drop your thoughts below, and don't forget to like, subscribe, and hit that notification bell so you never miss an update on the latest cosmic discoveries. Thanks for joining us on this journey through the ghostly sea of neutrinos, and remember, the universe's greatest secrets are still out there waiting to be found.